Hi there, I'm Dan Jones. Welcome to the podcast. Here I have conversations with people whose work intersects with climate in some way. I'm an oceanographer working at the British Antarctic Survey, and I started this podcast a couple years ago because I love talking with and learning from other researchers. Today, I'm very excited to bring you a clip from my conversation with Professor Scott Denning. Scott is a professor of atmospheric science at Colorado State University. I met Scott while I was doing my PhD out there at CSU, and although I didn't work with him directly, he was always very friendly and supportive of my work. Over the years, Scott has developed what is probably my favorite way to quickly and concisely explain the basic problem of climate change. In short, he talks about climate change as being simple, serious, and solvable. It's simple in that it's easy to understand the basics. It's serious because the costs of inaction are extraordinary, and it's solvable because there is something that we can do about it. Scott's message, it doesn't downplay the severity of the challenge of climate change, but it also doesn't succumb to defeatism. And Scott is a dynamic person who is really good at holding a room with energetic, but still kind of approachable confidence. This bonus episode is essentially Professor Denning's quick explanation of this message, and I'm excited to share it with you. So let's go ahead, let's get into this clip from my full conversation with Professor Scott Denning. Here we go.
Just ask, you ever wonder why day is warmer than night? You ever wonder why summer is warmer than winter? Or Phoenix is warmer than Fargo? It turns out that the answer in all three cases is the same answer. Heat in minus heat out equals change of heat. Luckily, that's not the whole story, because there's heat going out too. You can see the heat coming in, but you can't see the heat going out. Heat going out is invisible. Infrared, redder than red.
The three S's of climate change are simple, serious, and solvable. I try to always present it in that order, and I give roughly equal weight to each of the three S's. So simple is how it works, serious is why it's bad, and solvable is what are you going to do about it. Mm-hmm. The simple thing, I think many people in our field have forgotten how simple the basic story is. Heat in minus heat out equals change of heat, right? This is the first law of thermodynamics. And when you put more heat into the earth than you let out, it warms up. And when you let out more than you put in, it cools off. And this is, it's true of a pot of water. It's true of a planet. It's true of anything in the universe. And that's really the fundamental reason why CO2 causes climate change and other greenhouse gases, is because you're slowing down the emission of heat radiation from the Earth, but you're not reducing the incoming radiation from the sun. So of course it has to warm up. So remarkably, this has been quite well understood for 160 years, and it's not something that sort of scientists dreamed up recently. In particular, I think there's a very widespread misconception that is actually fed by the way we teach about climate change, that first we discovered the warming, and then we did sort of correlations and figured out that there were sort of, ice age correlations. But that's not at all the actual history of the discovery of global warming. The discovery of the absorptive properties of the gases came first, long before the warming, by about a century. So we've known since the middle of the 19th century that CO2 absorbs right in the wavelengths that the Earth emits. And it was predicted in the 19th century that burning coal would change the outgoing radiation to the point that you'd have significant global warming. So this is not something new. It's not unexpected. It's absolutely consistent with virtually everything that people know about temperature.
Never mind Civil War era science.
Yeah.
Over here, you can call it Victorian era science over here.
Victorian, sure. Yeah, absolutely. The Victorians had this down. So think of it as like steam locomotives and petticoats and top hats. That kind of era of science. It's not quantum mechanics. It's not relativistic. It's not difficult to understand. It's a sort of grade school era understanding of science. So that's simple. Serious is, oh my gosh, it just gets worse and worse, right? So fundamentally, every bit of carbon that you burn produces CO2, and the CO2 is semi-permanent, right? So on timescales that we care about, on historical timescales, the CO2 will never go away. So when people say, how much warmer will it get? The answer is, it depends on the total amount of fossil fuel that's ever burned in history. And I think, again, people just don't understand this. Is it 1 degree or 2 degrees? It's however many degrees you want. And the only thing that matters is when you stop burning the stuff. Because once you've burned it, you're done. It's there in the air pretty much forever. I mean, thousands of years it'll go away, but it's not going to go away the year after you stop, or the decade after you stop, or the century after you stop. It's going to be around for historically forever. And the consequences of large amounts of fossil fuel emissions are absolutely catastrophic, right? If you don't stop burning it soon enough, you have things like repeated storm surge flooding of very, very densely populated cities. You have crop failures and famine and complete loss of ecosystems and all sorts of hydrologic changes that are almost certainly enough to cause economic catastrophe and perhaps collapse. So the consequences of failure, the consequences of failing to stop making it worse, are absolutely unacceptable. And we can explore this in some depth, but given the amount of time I gave to simple, that's probably enough to say about serious. We want sort of equal time for each of the three S's. So simple, heated minus heat out equals change of heat. Serious, it just gets worse and worse until you stop making it worse. And if you don't stop soon enough, it's economically catastrophic. And then solvable, it turns out, is not that hard to understand either. The solution is to stop setting carbon on fire. There's really not that much hard to understand here. You have to stop digging up carbon and setting it on fire so that you stop making CO2. Well, how do you do that? There's basically two ways. One is to live a decent life with less energy, and another is to make energy that doesn't involve setting carbon on fire. So the living a decent life with less energy means sort of smarter economic growth. It means energy efficient buildings and transportation and food production and all that kind of stuff. And then the making energy without carbon, obviously we know how to do that. In fact, the cheapest forms of energy that we have are all carbon free. But the legacy, sort of Victorian era energy system is still with us. Again, steam engines and top hats. We're still digging up coal and setting it on fire. We're still digging up gas and oil. But switching over to a non-fossil energy system, basically, again, two things. One is to clean up electricity, and the second thing is to make everything electric. So this is sort of counterintuitive, at least for people my age. We remember really crappy apartments of our youth that were baseboard electric heating that were just terrible, super expensive, very inefficient. But the new world, the 21st century, everything is going to be electrical, which is kind of bizarre. So, for example, I have a 100-year-old house here in Fort Collins, and I remodeled it about 4 years ago, insulated the crap out of it so that it's super tight and holds its temperature. And I have a air source heat pump, which is basically an air conditioner that runs in reverse in the winter. So it takes heat out of the frozen winter air here in Colorado and pumps it into the house, just like a fridge. And that is all electric. And then I run the electric off of solar, and I have a very, very low energy, carbon footprint, certainly for my house. I have an electric stove. A lot of people want to cook with gas, but it turns out induction ranges are at least as convenient, and the temperature is at least as controllable as gas, but you don't have like indoor air pollution, you don't have carbon, you don't have natural gas.
And it's just cool. You're using magnetic fields.
It's freaking awesome.
That's amazing.
You put a pot on the stove and you push a button and the pot gets hot and the stove doesn't. It's like magic.
Magneto, you can, you've got superpowers.
Yeah. So then there's one more interesting wrinkle here, which is that the trouble with an all-electric, all carbon-free energy system of the future is balancing supply and demand, right? So the sources of renewable power are not necessarily where the people are. Like wind is mostly in the ocean and solar is mostly in the desert, but neither of those places are where most of the people live. So you have to get the power from where it is to where the people want it. And you have to do it when they want it, right? So daytime is when the sun is up, but nighttime is when people turn the lights on and so forth. So some combination of transmission and storage has to be in there in the mix. And so people have worked all this out. The engineering of it is not even all that hard. I mean, yes, it's a 21st century problem, but it's hard like cell phones were hard. It's hard like the internet was hard. It's not hard like impossible. It's estimated that completely replacing fossil fuels with this sort of 21st century energy system of the future will cost us somewhere between what we spend every year on cell phones and the amount that we spend every year on cars. It's not cripplingly expensive. It's the level of spending that we already do. It's just redirecting the spending that we have. So this is totally a solvable problem as long as we and our children don't just stop doing new things, right? My grandparents' generation did indoor plumbing and rural electrification and fought the Nazis, and my parents' generation did the interstate highway system and the space program and the Cold War. And my generation did, computers and cell phones and the internet. And the next generation has to replace the energy system. And it's not harder than any of those things. It's not more expensive than any of those things. It's right about the level of like indoor plumbing, right? So yes, you will have to replace the energy system, but no, not only will that not crush the economy, failing to do it will crush the economy. You have to do this. So that's it. That's my spiel. Simple, serious, solvable, how it works, why it's bad, what are you going to do about it?
There you have it, a clip from my conversation with Professor Scott Denning. Thanks for joining us. I hope that you enjoyed that. The full conversation with Professor Denning will be available next week, if you're listening to this when it was released. Thanks again to Scott for your time and for your insight and for sharing your enthusiastic vision with us. You can find Scott Denning on Twitter at @AirScottDenning, AIR, and then his name, Scott Denning. And you can learn more about his message at simpleserioussolvable.org. No spaces, just all one kind of meshed up word. I'm at Dan Jones Ocean, and you can follow the podcast at ClimateSciPod. Thanks for reviewing. Thanks for subscribing if you have. And let me know what you think about the show. Give me some feedback. I appreciate that. The music for this bonus episode was produced by Walter Hanna, so thanks to Walter for that. That's all for now. Again, join us next week for the full conversation. Normally, I release these podcasts every 2 weeks is my usual target. Take care, stay well, and I'll talk to you next time. Bye-bye.